The fact that it's talking about reasonable things that you could imagine or perform on your own. So remember, there's this plunger that's pushing on a block. So the plunger has this kind of nondescript force that's going to apply to a block. Then there's marks A, B, C, D, E, and F. And there's another block sitting at E. And we're told that there's friction between C and D. And although they say this, and I'll read it to you in case you don't have it in there, but it says identical blocks 1 and 2 are placed on a horizontal surface, points A and E, respectively as shown. The surface is frictionless except for the region between C and D, where the surface is rough. Beginning at time TA, block 1 is pushed with a constant horizontal force. And they even underlined the word constant. That was awful nice of them. Now, right now, this minute, if you're taking notes, I would encourage you to take a blank sheet of paper out, separate from everything else, unless you have already begun making your cheat sheet. If you haven't, this should be something on your cheat sheet. Because it might not be clear to you what the importance of the word constant force is. But when they say constant force, they are immediately telling you a ton of pieces of information. For example, they are telling you immediately that you can use Galileo's motion equations. Because a constant force means constant acceleration. So that's the first thing. The next thing, constant force means force times distance equals change in kinetic energy. Meaning, if you have a constant force, then you can easily figure out how much the kinetic energy of the block changes. And force times time is going to equal the change in momentum. So if the problem ends up being about time and not distance, you can still figure out how fast it's going. Those are all the implications that occur the moment they say constant force. But I want to focus on this one for a moment. The knowledge that the speed is always going to have a linear change. That's what it means. A constant acceleration. The slope of your speed versus time graph is always going to be a constant. So when we're looking at this graph, that implication that it's a constant force immediately tells me that my graph will be filled with nothing but straight lines. No curves at all straight lines. Because any force that acts is a constant. There can be an abrupt change, and there will be because we know there's a collision. But when I start looking at, okay, I've got TB there, TC, TD, TE, and TF. And they're clearly, I think, trying to confuse me with having the time things spaced different than the things on the horizontal picture of the plunger. You know, why would they have them spaced like that? So weird. Well, because the thing's speeding up and slowing down. If these are all evenly spaced, A, B, C, D, and E, they're telling me it's not going to make it to each of those places in the same amount of time. So speed is here, and they were nice enough to give us some, some markings here so that we had reference. We don't have to know how fast it actually goes. We just need reference. So let's begin. I need to figure out what happens between TA, which is when the plunger extends, and TB. So I've drawn this first line there, and it tells me it's a constant horizontal force, which means that during this time, I'm expecting there to be a constant change in velocity. Now, I'm making this a nice big constant change in velocity. Why? Use up as much graph as possible. That should be something that you should consider. Because one of the things that's not clear about this is that the marks on the graph aren't specific. But I know that there's nothing in this whole ramp thing that's going to make the object speed up ever again. So this is as fast as it's going to go. Does that make sense? Okay. So, all right, I'm sorry. I didn't read the whole problem, and I probably should. It says block 1 is pushed with a constant horizontal force from point A to B by a mechanical plunger. Upon reaching point B, block 1 loses contact with the plunger and continues moving to the right along the horizontal surface towards block 2. All right, block 1 collides with and sticks to block 2 at point E, after which the two-block system continues moving across the surface, eventually passing point F. All right. On the axis below, sketch the speed of the center of mass of the two-block system as a function of time. Ooh. Did you guys read that the way I read that? They're trying to mess with us, and they underlined the words center of mass. Now the reason this is important, and I hope you're really listening now because this is the good stuff. What I just drew was what was happening to block 1. What's happening to block 2 during this time? Could somebody type me a message or something? As I suck espresso? Or is this one of those awkward moments where nobody answers the question and we wonder what's happening? Oh, wow. 3 chats. It's not moving, it's not moving, it's not moving. Right, which means if I make block 2 a different color and drew block 2's speed, it would just be down there. Like just chilling. So this is interesting. What does that mean for the center of mass? If block 1 had a big change and block 2 had no change, did the center of mass change? It means the center of mass of the system moving. Well, sure, because one of the blocks is moving. I mean, once this thing starts moving this way, the center of mass of the system right now is here, in the middle. That's the center of mass. When block A has moved to here, the center of mass will have moved to here. That's the middle. When block A has moved to here, the center of mass will move to here. Is it me, or does it look like the center of the system is moving about half the speed of the block that's moving? So I might be inclined then to say, all right, they want me to graph the center of mass of the system. Maybe I should make that like here in the middle. Now, truth is, it doesn't matter what we do here, as long as we understand that we're talking about the motion of the center of mass and not the motion of the mass itself. The reason that's going to become important is they collide in a minute. So you can choose to still have it up here at the top, but you need to be thinking that if I choose to make this still the velocity of the center of mass, I need to be careful that I know what's happening to the center of mass. So I'm going to continue to graph what's happening to block 1 and what's happening to block 2 separately, so that we can kind of watch what happens to the center of mass. Now, let's keep going. From B to C, there's nothing there, so block 1 just kind of goes straight. You know, it has no change in its velocity. And I'm pretty sure you'd all agree that the other block doesn't move either, so nothing happens there. But at C, we hit the rough patch. Is anything going to happen to block 2 at the rough patch? Does block 2 actually even make it to the rough patch? I don't think so. So block 2 is just going to be, still doing the same thing, just going like that. Nothing happens to block 2 until block 1 hits it. On the other hand, when block 1 hits that rough patch, its velocity is going to change. I don't know how much. It doesn't matter how much. I just need to put down that the block's velocity changed. And it changes it to constant because the force of friction is a constant. Now, it's going slower. So that's why in the next interval, which there's no friction, block 2 still doesn't move. But block 1, it goes back to moving at a constant. Oops, I want to keep the lines the same color. There we go. Now, what happens when block 1 makes it to point E? That's right, Sophia. We can't hear you, but that's okay. If I was to say what Sophia was saying, but not being heard because she lost her voice earlier this week, so she couldn't, she was talking, but we couldn't hear her, is that there's a collision that takes place. Collision, that's right, it hits block 2. And they join together, so they now have the same velocity. Now that happens like immediately. So the moment there's the collision, all of a sudden block 2 increases its velocity, and block 1 decreases its velocity, but now they have the same velocity. Now, again, this whole line here has been what's happening to block 1. This line down here has been what's happening to block 2. The center of mass is what's happening in the middle of all this. So if I want to start looking at the center of mass, it was constant during this time. It has to be in the middle of this for here. And then the center of mass continues. At the collision, they are the same. So the blue line ends up being the motion of the center of mass when compared to block 1 and block 2. Now that's a tough question. Notice all of the things it combines together. It combines the idea of the center of mass, your ability to deal with constant forces acting on objects, and all of it in one graph with kind of arbitrary markings on it. But it took us